Hi there, welcome to my video on elementary differential equations. This is video number 3 for chapter 7, and the topic for the chapter is on systems of two nonlinear differential equations. The goal of this video is to study the behavior of the nonlinear system in a small neighborhood of a critical point. The key idea is the following. For a nicely behaving system, then in a small neighborhood of the critical point, the nonlinear system would behave in a similar way to a so-called linearized system. Now let's discuss a linearization of a nonlinear function. To begin with, let's consider a scalar function. Let's call it f of x. And let x naught be a root such that f at x naught is 0. Okay, so here we linearize at a point that is a root, x naught, but the linearization process is not restricted to that. You can also do it for any point x bar. Okay, so here are some assumptions on the function f near the point. We assume that f is smooth near x equals 0. That is, the derivative there is continuous. So we see that in that case, we can approximate the solution nearby with a straight line through the point x naught with the slope equal to the derivative of the f at x naught. Now let's visualize this. Let's say we have a function. Let's draw. And this is x. Okay. And this is the y. This is the function f. Assuming that x naught is 0, then the function f, let's draw that in blue. Let's, for example, it goes like this. And that's a point that is our x naught. And assuming the function is smooth, then in this small neighborhood around here, let's say a small neighborhood, this is our small neighborhood, then I can draw, let's say I draw it in a dotted line through this point and in the tangent direction. So you see, if the neighborhood is sufficiently small, let's say a neighborhood like that, then the solution is well approximated by this straight line. Okay? And therefore, in a neighborhood of x naught, the function f can be approximated by the function describing this straight line. So meaning it will be a function taking also 0 value at x naught and having the same slope as the derivative of f at x naught. Okay, so and that shall not be too difficult in function to write out. So the function would be a straight line, so a first order polynomial, which is 0 at x0. So when x is equal to x0, this is 0, I have 0. And the slope equals to f prime at x0. So it will be this function here. Okay, so the idea can be extended to vector-valued function. Using our notation, let's consider the 2x2 system. X prime equal to a function of capital F, and y prime is a function of capital G. And now let's say the point x naught, y naught is a critical point. That means f evaluated that is 0 and g evaluated at that is also 0. And then we intend to linearize this nonlinear system at this point, which is a critical point. So recall the on the previous slides, the linearization for a function, and we need the derivative of the function at the critical point. And here we have a system. So it's a more complicated understanding of the derivative. So here all the derivatives will be partial derivatives, and we have several of them. So let's introduce a concept called the Jacobian matrix, which is a matrix that collects all the partial derivatives, first order partial derivatives. Okay, so J at xy is defined as a 2 by 2 matrix, and for the first row here is about the function capital F, and you take the partial derivative in x, and then here you take the partial derivative in y. Okay, and they're evaluated at the point x and y. And then the second row collects the partial derivatives of g in x and in y. So here you have a collection of all the first order partial derivatives of the right hand side function. And such a matrix can be used to serve for the purpose of the derivatives of the vector valued function. Okay, now we can linearize the system in the same way as for a scalar function, simply replacing the unknown into the unknown vector and the derivative into the Jacobian matrix. Okay, so here's the linearization. So xy now is a vector derivative, which means is the derivative of the first and the derivative of the second, forming a vector. That equal to the Jacobian matrix evaluated at the 0, the point you are linearizing, times, and this is the 2 by 2 matrix, okay, times the vector minus the initial vector. So this is the vector, a general vector, and that's the vector at the, not initial, the critical points. So I have x minus x naught and y minus y naught. So if we compare this to the linearization of a function, recall that is f prime at x naught, x minus x naught. Okay, so you see the similarity. Now, since the solution behaves similarly to the solution of this linearized system at a small neighborhood of the critical point, then we can classify these critical points as different types and analyze the stability by our knowledge for the linear system. Okay, so we know that such properties are determined by the eigenvalues of the Jacobian matrix, of this matrix here. Okay, let's take an example. We see that we revisit an example we did from previous lecture, and the right-hand sides are factorized, and we have already identified critical points. Okay, so let's write out the 4 critical points we have found. One is 0, 0, and the second -2, -2, and then 0, 1, and 3, -2. And we wish to understand the type and the stability of these critical points. Okay, so we see that we need to find the Jacobian matrix and evaluate the Jacobian matrix at these critical points and finding the eigenvalues. Okay, so let's call this function capital F and this function capital G. So let's do the partial derivatives. F partial x, what would that be? Well, you would differentiate this in x. You can do the product rule, differentiate the first one first. You get -1 times that, and then you differentiate the second term. You get a -1, then it becomes a +1 of that, and adding them up collect like terms, and that's what you have. And then similarly, you do f sub y, differentiate this in y, and apply the product rule. And you will get 1 minus 2y. Okay, and for the function g, you can do similarly. Differentiate it in x, you get 2 plus y. And if you differentiate this in y, you just get an x. Okay, now we can collect these partial derivatives and form the Jacobian matrix. So this will be fx, and this is f sub y, and g sub x, and g sub y. And we see that because this is a nonlinear function, then the Jacobian matrix depends on the unknown x and y. Okay, so the next step is to evaluate the Jacobian matrix at the critical points and compute the eigenvalues. So let's repeat the Jacobian matrix here. So the first critical point is 0, 0. X is 0, y is 0. What is the Jacobian matrix? Well, one set x to be 0, and then set y to be 0. Then we get -1 and 1 and 2 and 0, which is here. And then we can compute the eigenvalues for this 2 by 2 matrix, and you find out that lambda 1 is 1 and lambda 2 is -2. So one eigenvalue is positive, the other is negative, and they are real. Therefore, we will have a saddle point, and such a critical point is unstable. Okay, and let's repeat the process for the second one. Second critical point, -2, -2. So you put x to be -2 here, and you put y to be -2 here, and you have the number. So there we have -5, 5, 0, -2. And so this is tridiagonal, and you know the diagonal elements will be the eigenvalues. So lambda 1 is -5, and lambda 2 is -2. So there are two negative eigenvalues. Therefore, this is a nodal sink. Okay, it attracts all nearby solutions, and it's asymptotically stable. Now let's look at the third critical point. X is 0, y is 1. So if we put it in, x is 0, so we have 0 here, and then y is 1, then we have 1 here. We will get -1, -1, 3, 0. And if you try to find the eigenvalues, and you see that the eigenvalues lambda will satisfy this quadratic polynomial, and you can easily compute that the eigenvalues here are complex and the real parts are negative, and therefore this point is a spiral point, and all the solutions will approach that in a spiral fashion, so it's asymptotically stable. Okay, finally the critical point number 4. That's 3, -2. So we're putting x to be 3, y to be -2, and this is what we get. And it's in a diagonal form, therefore the diagonals are the eigenvalues, so 5 and 3. They're both positive, which means nearby solutions will go away from the point. This is called a nodal source, and therefore it's unstable. Now let's consider our second example. And here is the system. It's also one system that we have done before, and we have calculated the critical points. Okay, so from a previous example, we know there are two critical points, 0, 2, and -1, 6. So we know that the procedure to carry out the calculation is the same as example 1. So we need to compute the Jacobian matrix. The Jacobian matrix here, a collection of the partial derivatives. So differentiate this in x, we get y minus 6, which is here. And then differentiate this in y, we get x, which is here. And for the function g, if we differentiate this in x, we get y minus 2, which is here. And you differentiate this in y, you get x plus 1, which is here. Okay, so let's evaluate the Jacobian matrix at the critical points. The first point is 0, 2, x is 0, and y is 2, so we get -4, 0, 0, 1. and it's a diagonal matrix, and the eigenvalues are on the diagonal, so it's -4 and 1. So one is negative, one is positive, giving us a saddle point, which is unstable. And now the second critical point, -1, 6. So x is -1, and then y is 6. Okay, so they give us 0, -1, 4, 0. And finding the eigenvalues, we see that it's pure imaginary. It's a positive -2i. So in this case, the critical point is a center. It's stable, but not asymptotically. So nearby solutions will circle around in a periodic fashion. Okay, so finally, let's consider our application in population dynamics. Let's consider the prey-predator model, the Lotka-Volterra system. Okay, and let's give numbers to the coefficients. So this is for the x, and this is the equation for the y prime. And we see that we can have two critical points. One comes from x0, y0, and the second comes from this factor 0, so y is 2, and this factor 0, x is 6. And the next step is to form the Jacobian matrix. So collecting the partial derivatives, so differentiate this in x, we get 10 minus 5y. And differentiate this in y, we get -5x, which is here. And then for this one, differentiate this in x, we get y, which is here. And differentiate this in y, we get -6 plus x, which is here. Okay, so let's keep the Jacobian matrix on the top, and let's evaluate this at the two critical points. So at x is 0, y is 0, these will all be 0, and we'll just get this diagonal matrix, and therefore the eigenvalues are on the diagonal. And here we put lambda 1 to be the positive one, and lambda 2 is the -1. And then we see that it's a saddle point, it's unstable. So what is the physical meaning of the point 0, 0? That is the state where initially there are no population present for either of the species, no prey and no predators, and therefore nothing will ever come to life if that shall be the case. But if you are in a small neighborhood around it, then the system behaves as a saddle point. We see that in the direction of the first eigenvector, the solution would go away from 0. So population would grow. And then in the direction of the second eigenvector, which will compute very soon, then the solution will approach the origin. Okay, keep that in mind. Let's compute the second critical point. And the Jacobian matrix will be x is 6 here, y is 2. We put that in, and then these two are 0, and we get 2, -30. And we found that we have two pure imaginary eigenvalues, and therefore this point here is a center. It's stable but not asymptotic, so solution goes around it in a periodic fashion. Okay, so how exactly does the solution go around the second critical point? We see that we need to gather some information from this first critical point, in particular the eigenvectors associated with lambda 1 and lambda 2. That will give us some idea of how solution would move around. Okay, so this calculation is to facilitate us to get more knowledge about more detailed behavior. We computed the two eigenvectors, and we see that v1 is in the direction of x, so is 1, 0, and v2 is 0, 1. So What does that tell us? Well, remember, lambda 1 is positive, lambda 2 is negative. We can now sketch in a small neighborhood at the origin. Let's draw this here. So this is x1, or we call it x, and okay, that's x2 here. Okay, and this is a critical point, and we find out that this is v1, first eigenvector, and this is second eigenvector v2. Now let's draw in red of how the solution behaves. So this is a saddle point, and we know that lambda 1 is a positive eigenvalue, so the solutions will go away. And then lambda 2 is a negative eigenvalue, so the solution will approach the origin. Okay? And then in a neighborhood, so we're interested only in positive solutions. So we'll be looking at first quadrant. How do the solution in the first quadrant behave nearby? So in nearby, we see it behaves as a saddle point. So it will go around like this, going in those directions, pointing counterclockwise, kind of a rotation movement. Because we're thinking that there is a another critical point here, which is a center. So solution nearby will be going around in the periodic fashion, right? It goes around in the periodic closed circle. So how would the solution move along this circle? Is it clockwise or counterclockwise? Well, we can get the information from what we have just done for the first critical points. We see that there the solution must move down from x2 and move out in x1. Therefore, all these will be going around in counterclockwise. Okay, so finally, let's present the solution for this system calculated in MATLAB. We plot it, and we see that the solutions are circles, meaning not exactly the circle in a circle. It's a closed loop. Okay, and we see that two critical points, one is here and the other one is here, and we see that here the solution would behave in this way, and therefore you go around in a counterclockwise. So I call these circles of life. So life goes around and around. So what really happens here, you can think as following. When you have, for example, when you have a lot of predator here and a few prey, and then the predator's population will decrease because it doesn't have enough food to eat, and it will decrease to a very low level. Once it reached a certain level, then fewer prey will be eaten by the predator. And remember, the prey has a population that grows exponentially if the predators are not there. So the predators are so little, so the prey start to recover, and it grows exponentially. So it grows pretty fast. Okay, so once you have more prey, then the predator has more food, and it starts to eat the prey, and the predators start to recover and start to grow. Once the predator grows into a certain population, then the rate it can eat the prey will be higher than the rate the prey can naturally grow, and then the prey will decline. But still there's plenty of prey, and the predator population still grows until it reaches some point that the food source is getting sparse, and then the prey population goes down because it doesn't have enough food, and the predator also goes down. So they both go down, and then the cycle continues. Okay, so I hope you enjoyed this video. That's all I want to say. The next video will be an additional video. It's not really strictly needed. It's a detailed study on the competing species system in the population dynamic, which we will observe very complicated behaviors. Okay, so that's all for today. I hope you enjoyed it, and see you next time.